Hello there, and welcome to Forces 1 Part 1. This is going to be on Lesson 3, which is Resultant Forces. Right, so before we get started, just make sure that you are aware that there is some higher tier information in this lesson. So I'll be making sure that whatever is higher tier has a note on it so that if you don't need to learn it, then you can just skip forward to when that note little thing disappears. But we're going to be looking at resultant forces today. Which is going to work off of the previous lesson that we did when we were learning about vectors. Okay, and as with always, we're going to start off with a do now. So 8 questions. Most of these will be based off of what we were doing in the previous class. So go ahead, pause the video, and answer these questions. Right. So I'm going to show you the answers. Make sure you have a green pen and you are putting down the correct answers. And there you go. So for today's lesson, we're going to be looking at resultant forces, which have to come from free body diagrams. So I'm going to explain a little bit about free body diagrams, but at the same time, you do need to realize that what we're working with today are all going to be basically vectors. So if you need a basic refresher from last time, go back to lesson 2 and just skip to the places that you need to revise a little bit, and then you can always come back to lesson 3. So the first thing we're going to learn about here is free body diagrams. So starting on line 3, it says that we can represent forces using a force diagram, which shows the forces acting on an object. And as we learned last class, vectors have a direction. And so the direction of the arrow shows the direction of the force, and also the size of the arrow represents the size of the force. So we're going to highlight that bit right there, and you should know this because last time we talked about how the longer the arrow is, the bigger the force that's being applied. And also we have forces going in different directions. But really, we are only working in four directions right now. So we have our horizontal and vertical components. And if you look at the diagram on the right here with the black circle, the weight is larger than the drag, which means that this object will be going down, all right, because the weight has a much larger force than the drag. Okay, so depending on which side has the strongest force is the direction that it will go in. Now, looking at resultant forces, if you're looking at a free body diagram, like the one that we just saw with the black object, you have 2 forces acting on an object, right? And those forces are acting in opposite directions, and we said that the weight is greater than the drag force. When you add both of these, right, they would result in a single force going downwards. And so that's kind of an interesting way to word it. What I would say is if they're working in opposite directions, then you would have to subtract those 2 forces. All right, so you can put on any numbers there, but really your weight should be bigger than your drag. So you can put in an example of saying that your weight is 10 newtons and your drag is 7 newtons. So then your resultant force would be 3 newtons going downwards. All right, so that's your resultant force. And your resultant force is always going to be just one force, a single force that has the same effect of all individual forces acting on an object. So you can have 4 different forces acting on one object, but your resultant force would generally be just one force, and it would show you the amount. So how strong or what the amount of the force is, and also the direction. So remember that we're working with vectors. So after all the individual vectors have been added and subtracted depending on if they're going in the same direction or in opposite directions, like I said, the resultant force is only one arrow, all right, and it is an account of all the forces that are acting on that one object. So if you read the checkpoint question, it asks, well, what is the name given to the single force that is equivalent to all other forces acting on a given object? Like we said, that is your resultant force, all right? So when we talk about free body diagrams, we have what's called balanced and unbalanced forces. So you might have a book on a table right now, or even look your booklet that you're working on right now, and it's resting on a table. If it's resting on a table, there's going to be 2 forces acting on that book. All right. You have your weight, which is due to gravity, right? Gravity pulls us all down, but you can realize that it's not going through the desk, right? And so there has to be some sort of reaction force that counteracts that gravity. And so what's happening is the table is actually applying the same amount of force in the opposite direction so that your resultant force is 0. All right. So if you have two forces that are going in opposite directions, but they are the same amount of force, then we say that those forces are balanced, and your resultant force is going to be 0. Now, in this case, um, the book isn't going anywhere, and you know that, so you're actually going to have um, no movement at all. And I'm going to explain a little bit about why there is a force going upwards, because it doesn't look like that at all. In your head, you know that gravity pulls everything down, all right? But you don't actively see anything going the opposite direction. So this is actually due to a famous physicist, and you probably know him by the name of Isaac Newton. He wrote down 3 laws of motion. And the third law has something to do with why there's a force going upward. So he says that to every action, there is an equal and opposite reaction, right? So the best way I can explain this is using a rocket, right? A rocket applies a force going downwards, okay? But Newton says that if there's a force going downwards, then there must be a force going upwards as well. And this is actually the reason why rockets are propelled upwards, all right? Because rockets exert a tremendous amount of force going downwards, and that force needs to be strong enough to lift the entire rocket, its weight, and also more to propel it upwards. Okay, so not only is it resisting resisting the force of gravity, but it's even greater so that it keeps accelerating upwards. All right, so that's Newton's third law of motion. The other law that pertains to why this book is stationary is Newton's first law. And that explains motion of an object does not change as long as the net force acting on an object is 0. So that net force is really the resultant force. Okay. If an object is at rest, it will stay at rest unless something acts on it. And that kind of seems a little bit silly to say, but once it's in motion, right, depending on what the force is that's acting on it, the acceleration or the velocity of that object might change. And we're going to look at that in the next one here. All right, so now we have a skydiver, and I think this goes without saying, but you know that if a skydiver jumps out of a plane, he will be falling towards the earth. All right, and you can see on the diagram that there's 2 forces. You have the weight, again, due to gravity, and you have air resistance, okay, because he's not a straight object like a pen or a pencil. He is experiencing a bit of air resistance due to the air molecules. So, both forces have the same magnitude, but they act in opposite directions. All right, so that's quite important here. And so we still have balanced forces, but you know in your head that if a skydiver jumps out of a plane, he's going to be moving down. So why is the weight not larger than the air resistance? Okay, because if you know that what I told you is that if you have a larger force, right, it's going to move in that direction. So here's where that kind of misconception comes in. These forces are said to be in balance, but the resultant force is still 0, and the skydiver is actually moving with constant velocity. All right. So it says that the object is in motion even if the net force is 0 and will remain in motion with speed and direction. The only difference here is that this skydiver, if both those forces are the same, he's not going to accelerate. Right? So going back to Newton's first law, right? The motion of an object does not change as long as the net force acting on the object is 0. So if that if that object is already in motion, as long as those forces are the same or the net force is 0, then that object will stay in motion, okay, unless there's a bigger force or a less force acting on it. All right, so we say that whatever object we're looking at is moving at constant speed, okay? So even though the forces are the same, in physics you do have to account for what's the setting before we look at a specific point in time. Okay, so if you see that the car is moving, but the forward force and the backwards force is the same, then you can safely say that that car is moving at constant velocity. All right, it's not accelerating. So that only changes if the forces are unbalanced, and that's going to be our last one here, where we have forces acting on a box. And you can see right here that the force going to the right is much greater than the force to the left. And these forces, again, are going in opposite directions, and we say that these are unbalanced. So in this case, the resultant force is not zero. It's actually a certain amount of whatever number it is towards the right. And if you have unbalanced forces, then what happens is you have acceleration, okay? And likewise, if I reversed these arrows, right? So if we were looking at a car and your backwards force, right, and we're going to call that drag, becomes greater than your thrust, or the forward force, then it will decelerate and slow down. So the picture that I have at the bottom here, oh sorry, let me just say that this box right here, it's going to accelerate. But you'll see at the bottom here that the top 5 arrows, all right, has the same velocity. And so for those 5 objects right there, or 5 cars, the forward force and the backwards force, or the thrust and the drag, are all the same. So the net force is 0. But when you have a car that shows the same forces as the box up here, where the thrust is much bigger than your drag, then that car, every time you look at it, if the forces aren't changing, then it's going to continue to accelerate or get faster and faster and faster. All right. So let's quickly answer this checkpoint question. When forces acting on an object are balanced, what can be said about the resultant force? So if they're balanced, all right, the resultant force is going to be 0, all right, because they're in opposite directions. Right, so now we have some practice problems. We have a runner in the diagram, and he's in a position, he has 2 forces acting on them, and it's 40 newtons to the right and 40 newtons to the left. So remember that you have 2 forces in opposite directions. And number 1 asks, well, describe those 2 forces. If you want to go ahead and pause the video, you can answer numbers 1 to 5, and then we'll go over those together. Perfect. So those 2 forces we say are balanced because both forces are exactly the same. All right. And number 2 says calculate the resultant force on the runner. Now, hopefully you shouldn't need a calculator for this, but if you have 2 forces that are going in opposite directions, then you have to subtract them. So 40 minus 40 is going to be 0. Number 3 asks, when the starting gun is fired, the runner uses their muscles to apply a forward force of 80 newtons. And so you have to calculate the resultant force if the backward force is still 40 newtons. So now the diagram has changed. The forward force goes from 40 newtons to 80 newtons, but the backwards, the drag, is still 40. And so you're not really changing your process, you're just changing the numbers. So you have to say that the resultant force is going to be 40 newtons. And I did forget to, or maybe I didn't. Number 4 says suggest the direction of the resultant force, and that should be in the direction of the greater force, and that's going to be to the right. So if the question does not ask it, you can assume that if it's asking for a resultant force, you do have to include the direction because force is a vector. And so with vectors, it both has a magnitude, so the number 40, as well as direction. So you have to specify that it is to the right. Number 5, as the runner gains speed, the drag forces increase to 70 newtons, and the runner maintains their 80 newton force from their muscles. Calculate the new resultant force acting on a runner. So now, again, the numbers have changed. Your forward force is still 80 newtons, but your drag has increased from 40 newtons to 70 newtons. Same process, different numbers, and what you have to do here is subtract 80 and 70 from each other, and what you get is 10 newtons, and again, don't forget the direction, that is to the right. So what this means is that this runner, all right, since the resultant force is much less, that means that they are not accelerating as fast as they were before when the starting gun went off. There's one more question on the back page, or on the next page. There was number 6. When the runner crosses the finish line, they apply a braking force on the ground, and it gives you those numbers there. And you have 70 newtons of muscle force and 40 newtons of drag. So again, if you draw the arrows and do the calculations, you should get 30 newtons to the right. All right. All right, now you'll notice in the top left corner there is an HT there, so that means that from this point it will be higher tier. So if you need to skip ahead, because there is a portion towards the end of the video that is not higher tier, you'll notice that the symbol in the top left corner will disappear. So just skip to the point where you no longer see the higher tier button on the top left. But in this activity here, we are going to be drawing free body diagrams, and this shouldn't be honestly too hard, but take some time, read the questions, all right? I'll do the first one with you, and then I would like you to try the other two questions by yourself. So number one says, draw a free body diagram to show the forces acting on a book that weighs 40 newtons on a table. So you're given a situation where you have a book on a table and you have the weight, all right, that's 40 newtons. So the first thing you should do is always draw the object that you're focusing on. So you can draw a book, a rectangle, whatever, all right? And if it's weight, all right, you should know from there that that weight is due to gravity, and gravity always goes downwards. So your free body diagram should look like this, all right, so far, because you have 40 newtons going down. Now, if it's resting on a table, right, remember that Newton's law says that if there's a force, right, for every force, there's an equal and opposite force as well, and it's resting on a table, all right, so there has to be 40 newtons going upwards as well. Okay, so then now you have a stationary book that is resting on a table. So there's number one for you. Number 2 and 3 are asking you to do the same thing, but with different scenarios. So number 2 is asking, well, if the book is picked up and then dropped on the floor, draw the free body diagram when it is falling. And number 3 is just asking for a plane that's at cruising speed and it has 4 forces acting on it. So make sure you're labeling your 4 forces for number 3. All right. And go ahead and answer these questions. You can pause the video right away. Right. So for number 2, the book is picked up and then dropped. So if it's falling, all right, then you should have really just one force, okay? And that's going to look like this. So you still have the same object, but there's no force going upwards. You could have air resistance on there, but for the purposes of this learning activity, we're not going to add it in, all right? And you'll see why in a little bit here, okay? Number 3, a plane flying at cruising speed at altitude has 4 forces acting on it, and these forces are weight, upthrust, thrust, and drag. And it's asking you to draw the free body diagram to show all the forces acting on that plane at constant speed and altitude. So key word here is that it is acting, at constant speed. Okay. You can use a square box to represent the plane, but I just found a picture of a plane, and you should have 4 forces acting on it. So again, constant speed and constant altitude, which means that all 4 forces should be exactly the same size. All right, and it looks like I forgot to put in the labels on it. So the arrow going to the right should be your thrust, because that's the direction that the plane is going, which means that your drag will be the opposite direction. The other two should be quite simple, because you know that weight is going downwards due to gravity, and your upthrust will be the force that is opposite to weight. Okay. Right, so number 4, so here's part of the reason why I had you hold off on this. For number 4, for each of the above examples, questions 1 to 3, draw the resultant force acting on the object. So number 1, remember, was the book resting on the table. All right, so if it is resting on the table, then the resultant force should be 0. Okay, they're working in opposite directions of the same amount, same magnitude, which means that the resultant force will be 0. You just subtract them. For number 2, right, remember that our free body diagram only had 1 force on it, and if it has 1 force, then that makes your job kind of easy, because your resultant force will be that 1 force, okay, because there's only 1 force acting on it. Number 3, we have the plane that was at constant speed and constant altitude. So same thing, you start off with your object, and because all 4 forces were exactly the same, you can look at it as 2 forces and 2 forces, the ones that are working in opposite to each other, but since they're all the same, really, you're going to get a resultant force of 0 again. Okay, and that goes back to the skydiver. Remember how he was falling, but the 2 forces were exactly the same, which means that your plane here is traveling at constant velocity. Okay, number 5, the plane opposite has 4 forces acting on it, and draw the resultant force acting on the plane below. So let's start off with the easy one, okay? You have 10,000 newtons going up, so that's your up thrust, and 10,000 newtons as your weight. And since those two are acting in opposite directions, that means you subtract them. So really, you should have no vertical components in this diagram, okay, because they're exactly the same. So they're going to cancel out to zero. Now, looking at your thrust and drag, you can obviously see that they're different, okay? And when they are different and working in opposite directions, then you're going to subtract them. Now, after you subtract them, that number that you get, the next step is figuring out, well, which direction is it going? And like I said before, it's going to go in a direction that has the bigger force. So in this case, it's the 58,000 newtons. And when you subtract 12,400 from it, then you get 45,600 newtons to the right. Okay? So there's your answer there. And remember that resultant force will always be just one force. Okay? So quite lucky here that your up thrust and your weight are exactly the same, because then we would have to work with diagonal forces. Okay? Last thing, question 6, from question 4, above two of the resultant forces were 0. In each case, describe the motion of those objects. So this is the reason why I had you not put a upward force on number 2 when the book was falling. And the reason is because number 1, it's a book resting on a table, so you know that that's stationary. Same as number 3, it's moving at constant speed, even though the resultant force is 0. And this is the reason why I had you not put a additional force there, because we should have one that is in motion, okay? Or I should say accelerating. All right. Okay, so now we're getting to a little bit of the more complicated stuff. What I've told you before is that forces go in horizontal and vertical components, right? So they go up, down, left, and right. You can have forces that go diagonal, right? Because it should be pretty simple that we all don't move up, down, left, right. Okay, we can move diagonally, we can move in curves, stuff like that. So forces, when we're drawing free body diagrams, we can do that as well. And you have what's called the parallelogram of forces. Okay, so there's 5 steps to it, and on the next page you have some practice to do. The first, and they're all labeled by numbers. Okay, so what you're going to do, if you have a diagonal force, you're going to draw the horizontal and vertical components. Okay, and by the end of it, you should have a parallelogram. Okay, that kind of looks like a diamond. So if you follow the steps here, you have 1, 2, 3, and 4. All right, and really what you're doing is you're getting the number 1 and number 3, right, should be the same on the right, and number 2 and the third one on the top should be the same. Okay, and that will make your parallelogram. So let me show you what it looks like in practice. Right, so on the top left, you have 2 forces, okay? And so what we're going to try and do is create the resultant force from these 2 forces. When we compensate, or when we account for those 2 forces, you should get one really big force. So what we're going to do is we're going to look at the horizontal line, okay? And we're going to copy that, and we're going to move it up and connect it to the top of that diagram. So it's going to look like this. So that purple line there should be the same length as your horizontal. Next, we're going to move the line going diagonally, okay, and we're going to move it across, same length, and we're going to attach it to make our parallelogram. Okay, and then the only thing that we have to do from here is connect the 2 corners together. So then this red line here is your resultant force. Okay, so hopefully that makes sense. I'll try one more with you and see if you can do the other 2 by yourself. So again, you have 2 lines, so really what you want to do is you want to copy those 2 lines, same length, right, same angle, and you just really want to shift them over so that you have a parallelogram, okay? And then the third step from there is really just connecting the 2 corners together so you have your resultant force, like that. So go ahead and try and do the exact same things to the bottom 2 diagrams. Pause the video and I'll show you what it should look like. Good. So by the end of this, your bottom left one should look like this, and your bottom right one should look like that. Okay, I went off the page a little bit there, but hopefully you have enough room. I forgot to mention, I apologize, that you should be using a ruler for this. You don't want to freehand this because then your angles will be slightly off. And if you're looking for perfection, then using a ruler would be your best friend. Okay. Right. The only thing here is figuring out, well, now that you have a force that's going diagonally, all right, your resultant force, we should be able to calculate, well, how big is that force, all right? So every single force can be resolved into two components acting at right angles, okay? So what we're going to do is we're going to be looking at right angles, right? And that's going to be 90 degrees. So you have your green and your red, all right? And so what I'm going to do is I'm going to label this as A and B. Okay, so A and B are your horizontal and your vertical components. And not quite sure if you've learned this in maths or not, but if you have your hypotenuse of a triangle, which is the angle one, if you have that, then you should be able to apply a theorem called Pythagoras theorem. And Pythagoras says you can figure out the length of the third side by using a squared plus b squared equals c squared. All right, so whatever your length for A is and whatever your length for B, right, then you can figure out your length for C. And so you can apply this in physics because if you know your force for A and you know your force for B, then you can figure out your force for C and you can actually figure out your resultant force, okay? There is a caveat, which means that there is a catch, okay? Pythagoras only works for right angle triangles. If you have, say, a triangle that is not a right angle triangle, then you cannot use Pythagoras theorem. Okay, so going on to here, okay, we are going to answer the top right one because this one is the only right angle triangle in there. All right. So we're going to use the same practice of using or drawing the parallelogram, except in this case, your parallelogram is going to look more like a rectangle. All right. So same thing. You're going to copy your horizontal axis and your vertical axis, right? Or your forces, I mean, and you're going to copy them and shift them over to make a rectangle. So it should look like that. And then same step, you attach the two corners to each other, and you get your resultant force like that. So then you're figuring out, well, where's the right angle? And your right angle should be on the bottom right of that triangle, okay? Now, each box in this grid is worth 1, okay? So if you count the number of boxes along the horizontal and your vertical, you should get 22 and 11. All right. Now, from these two, you're using the exact same formula, a squared plus b squared equals c squared, and you will get your red line, the length of the red line there. Okay, so after doing all that, you're going to get a squared plus b squared equals c squared. Just replace the numbers, right? 11 squared plus 22 squared, and hopefully you know how to use your square root on your calculator because you won't be able to do this in your head. You should get 24.6 as your resultant force. So that's the actual force of that red line in the middle of the square, or in the middle of the rectangle there. Okay, and that's how you're going to figure out most of your resultant forces. Okay, for the other three, remember how I said that Pythagoras theorem only works for right angle triangles? There is a way to solve these three, and this is the reason why this is higher tier, because you have to do 3 times as much work. So what you would do, really, is you would find out, you would make right angle triangles with each force, okay, that are going diagonally. So you'd have to do this triangle twice for each force, and then you would have to find out those 2 forces and then do the triangle one more time. Okay, so it's not going to be the most simple thing in the world, but it is possible, and the reason why I'm skipping it right now is because it is quite a bit of work. Okay, but if you have questions about that, you can always ask one of your teachers to solve it for you. Right, so this is the last slide on the higher tier information, and this is just basically drawing the components of a force. So far what we've done is we've gotten a force that's going diagonally, and we've drawn the horizontal and vertical components. What we're doing now is going the opposite way. All right, and so what you're going to do is if you're given a diagonal force, okay, you're going to be able to find the horizontal and vertical components. So we've narrowed it down to 3 steps here. Your first step is to do the x-axis. Okay, so put a ruler up to your arrow here on your force and have it parallel to your x-axis. Okay, or your y-axis, doesn't matter which order you do it in, and you're just going to draw a line straight down to your x. Okay, the next step is to draw the horizontal line which goes along your x-axis, and you're going to draw that until it hits your y-axis. Okay, so those two lines really should be the same as your x and y, right? Which should have numbers along them. So in this case, the blue two arrows, right, should be the same length, and your two red lines should be the same length. Okay, and the last thing you're going to get is four lines, right, and your diagonal. So really this is just working backwards from the diagonal force to horizontal and vertical components. That's all it is. Okay, so let's practice this a little bit. So you're given a diagonal component here, and this can be broken down into horizontal and vertical components. So like we did on the previous page, you're going to start off with your x and your y. Okay, so the two lines that I just drew there should be the exact same length, okay, that goes along your x and your y axis. All right, so those two lines should be along there. So the dotted lines are not your actual forces, okay, but the solid lines with the arrows are your actual vertical and horizontal components. The dotted lines are just there to help you along your axis to see what number it falls on. Okay, so for the rest of them, I'd like you to try them by yourself. All right, I'll show you the second one just to make sure that you are doing it correctly. So at the end of each diagram, you should have two solid lines with arrows and two dotted lines. Okay, so pause the video and go ahead, try the other four. They're all going to look quite similar, but different lengths, obviously. Right, so the other four diagrams should look like this. So there's your third one, your fourth one, fifth, and sixth. Okay, so depending on the size of your diagonal force, your vertical and your horizontal components are going to be very different. Okay, but this should be able to illustrate to you that every diagonal component can be broken down into horizontal and vertical components. Okay, so on the next page here, you have some scale drawing. So most of the time when you're given a diagonal drawing on a grid, you should be able to give me the actual numbers. Okay, so exactly the same step. If you have a diagonal force, you can either start with your horizontal or your vertical component, doesn't really matter. I'm going to start off with my vertical component first. So you're going to draw a line from the arrow, right, the tip of the arrow down to your x-axis. Okay. And then drawing your horizontal component, you're going to start from the arrow again and go along until you hit your y-axis. Okay. After that, since this is on a grid, you can actually figure out the numbers. Okay. So your red one is going to be 16 and your green is going to be your 20. Okay. If you count the number of boxes along that dotted line, you will get 20 and 16. From here, you can actually figure out your diagonal component here. So the black line there, you can figure it out. It should be somewhere around 25, 26, I believe. I'm not doing the calculations because the question says, using the scale drawing, find the horizontal and vertical components, right? So there's your horizontal and your vertical components, okay? I'll do the next one with you again, just to show you a different way of doing this. So what I did there is I kind of did everything all at once, but if you find that a little bit too confusing, you can always work one component at a time. Okay, so same thing, I'm going to start off with my vertical component, and you're going to draw a line from the tip of the arrow down to your x-axis. And then from there, you can count the number of boxes that that dotted line contains, which is going to be 7 in this case. So that's going to be your vertical component. And then you do the exact same thing for your horizontal. You start at the arrow again, and you go along until you hit the y-axis. And you count the number of boxes along that dotted line, and you should get 26. And so that's going to be your horizontal component there. All right. Right, so that's pretty much the end of the lesson there. Please make sure that if you did not have to do the higher tier information, that you go back and figure out the horizontal and vertical components, because it is quite important how you need to know how to do that stuff for GCSEs. All right, so at the end of the lesson, there's going to be a knowledge check, 10 questions. The last two are legacy questions that have to do with chemistry. All right, so just to make sure that you are brushing up on that sort of stuff every once in a while, go ahead and pause the video and answer the questions, and I will reveal the questions reveal the answers afterwards. Perfect. So here are your answers. Please make sure that you have all the correct answers on your booklet. Mark them with a green pen to figure out which component, or sorry, which parts that you are lacking in. And if you need to watch the video again, certain parts, feel free to do that. Go at your own pace, all right? Thank you for watching, and I'll see you in lesson 4.